Okay, here's a question. I'm going to pause the video after I've set it up. What I'd like you to try and draw is the acceleration from this acceleration profile. So starts off at the time of 0. We'll assume there's no offset displacement and we're not moving at the start. So at the start we're going to say that S equals 0, V equals 0, day equals 0. And then as soon as this starts, we get an acceleration. So I'd like you to draw the velocity time graph, and then using the velocity time graph, calculate the limits and try and draw the acceleration, the displacement graph for this. The displacement graph is actually also going to be a distance graph. So pause the video now, have a go at it. Right, coming back. So I'm going to try drawing it using, let's go into my purple. So the first thing to realise is this first block, we've got a constant acceleration, which means the velocity is going to move in a straight line, and we said we're starting with a velocity of 0. At the end of 1 second, the area of this tells you what speed we're doing. So the speed at the end of this is 4 meters per second because of the area inside. So at the end of here, we get 4 meters per second. We do a straight line growing to that point. Then the next phase, from 1 to 2 seconds, there is no acceleration. That doesn't mean there's no speed or velocity, but the acceleration has dropped to nothing. So the velocity stays constant. It's horizontal. Then we've got a period where we've got a negative acceleration. 2 seconds at minus 2 meters per second is minus 4 meters per second. That's the area inside that graph. So the graph over this period of 2 seconds drops 4 meters per second in speed. So that's your velocity profile. Now we're going to have a go at drawing the graph for the displacement. So before we start putting in the vertical axis, we need to know how far we're going. So what we do is the area under this curve is the displacement in that time. Doesn't necessarily mean it's a straight line, because it does very small amount of increase at the start and then a large amount at the end. So let's calculate the area of this section. So it's 1 by 4, halve it, that's 2 meters. That's the first region. The second region is an extra distance, which is 1 by 4, which is 4 meters. And then finishing off, we've got 2 by 4 and halve it. That gives us another 4 meters. So overall, we're going 10 meters. So we've got 10 there, now we've got 8. So let's say that's 10 meters there. So in 1 second, we get to 2 meters. At 2 seconds, we've got that 2 meters and another 4 meters. And on the way back, we've got 4 meters again over those 2 periods. So that's our key points. Between here, this section, the graph is being constant speed. And the little clue to you about how to draw the graph is, as this graph gets towards the end, it should be matching this gradient. So remember, the gradient should match as we go from one side to the other. So at the start we've got nothing, which is a horizontal gradient, so we get start and we slow curve upwards to join our constant velocity. At the end we've got constant velocity very close to the same, so it carries on at the same gradient and then starts slowing down towards 0 at the top end. And that's our 3 regions covering 10 meters. Okay. If you get changes in acceleration, you need to think, what does this mean when we come onto the displacement graphs? You may have seen sometimes an attempt to draw two curves matching when you've got a change of acceleration. They should, because the velocities are pretty much the same either side of that point, when they come onto this graph, they should have the same gradient when we connect. Okay, so the displacement graph should be smooth. So that's a acceleration to velocity to displacement graph.